Hello, everyone. Good evening. I hope uh, all of you are ready for a very nice dose of advanced mathematics this evening. Um, have with us Dr. Arka Banerjee. Dr. Banerjee is a researcher in geometry theory, and he's interested in quite a few parts of advanced mathematics like topology, group theory, and geometry, and so on. Today, he will be speaking on a generalization of the Cannon's conjecture. Um, Orko, you can whenever you're ready.
Thank you, Ashwini. Thank you for giving me the opportunity to speak here. Okay, so I'm going to talk about this about Cannon's conjectures. I'll tell you what Cannon's conjecture is, but before all that, I want to mention that everything that I will say is joint work with Kevin Shrivi. Okay, so before even stating the Cannon's conjecture or any new theorem, I would like to start with a more basic question. And towards the end of the talk, I'll come back to this question and tell you what it has to do with Cannon's conjecture. So this question should be understood by every one of you. So it goes like this. So suppose I give you this set S that has these 4 points in it. Okay, this 1, 2, 3, and A is a special point. I'll tell you why this is special later. So you have this 4-point set, and suppose you have a cyclic group Z3. So Z3 is a cyclic group of order 3, is acting on S. How it is acting? Well, what it does is, well, you take the generator of this cyclic group. So what A does is, so I have to tell you what it does to this set. So what it does is so I have 1, 2, 3, A. So what A does is A cyclically permute the first 3 points and fixes A. Okay, so if you hit 1 with A, it will give you 2. If you hit 2 with A, it will give you 3. And if you hit 3 with A, it will give you 1. Okay, so A cyclically permutes the set 1, 2, 3, and it fixes A. Okay, so that's the action of Z3. Okay, is that clear? So Z3 is acting on this 4-point set, this nice. So it is fixing 1 point and it is cyclically permute the other 3. And now imagine S as sitting inside a circle. So you have this circle S1, and now I have this set S sitting inside it in some way. Let's say here it's 1, here is 2, here is 3, and here is A. Okay, so this 1, 2, 3 doesn't have to be in this order. So just embed this set S in any way inside S1. Okay, this is one of the way that you can embed inside S1. So okay, so I haven't tell you what the question is yet. So the question is, so we already have an action of Z3 on S. Okay, so on these 4 points. So the question is, can this action, this particular action on this 4-point set, can this be extended to S1? Okay, so maybe I'll write the question now. Can the action of Z3 on S be extended to an action on S1? Okay, All right, so A is an homeomorphism on this 4-point set 1, 2, 3. It's cyclically permeates 1, 2, 3 fixes A. So basically, the question is asking this homeomorphism. Can this homeomorphism be extended to the circle S1? Okay, so that means can you find me an homeomorphism from S1 to S1 that restricts to an homeomorphism on this particular set, which match with this A. All right, so this is a particular, it's an understandable question, and so I'll tell you about the answer in the later part of the talk. But if you get bored in the middle of the talk, you can think about this question yourself. Okay, it's not too hard to see what could be the answer. You could probably guess that if you think about it for some time. But okay, I'll get back to this question. Okay?
So, Arka, can I ask
Yes.
you one question, because there might be some high school students here as well.
Oh, okay.
So,
Okay.
I just wanted to understand, maybe if you speak one more line. So, basically, what you were suggesting is that when you say action of Z3 on S, you are essentially suggesting that in the way you described, right? You
Yes.
are, it's basically permuting 1, 2, and 3.
Yes.
And when you
Yes.
say action is by fixing A, so when you say extend it to S1, so
Yeah.
basically then you would like to move around other points on S1 as well, uh, which are compatible with the way you moved around the points 1, 2, 3. Is that what you mean?
Yes, yes. So yeah. So probably I can probably phrase it in more nice way. So you have this map. So we all know what maps is. So you have this bijection map from this 4-point set to 4-point set. What it does, so it sends 1 to 2, 2 to 3, 3 to 1, and A to A. So this is the map from S to S, and now we want to find, so the question is there a map? Is there a bijection, bijective continuous map from the circle to circle? And remember, this S is sitting inside this S1, right? And so I want to find a continuous bijection map from S1 to S1 such that if you restrict B, such that if you restrict your B to that subset, this S1, you get the map E, okay, where A was this map. Okay, so that's what this question is asking. Okay, so yeah, if you don't know about action, you can probably ignore this. So yeah, so just to tease you about this question further, let me tell you the answer. Okay, but you can still find out why that is the answer. The answer is no. You cannot do that, and I can also give you a hint. The hint is 3 does not divide 8. This 3 is coming from this number of these 3 points, and this 8 is, somehow coming from that you have this total 4 points. 4 times 2 is it. But anyway, so we'll come to that at the end of this talk. So let's tell you about Cannon's conjecture. Okay, so it's a famous open conjecture in geometric group theory. So it roughly says that if you have a group which looks sort of like a hyperbolic group, so that means it has some features of negative curvature, then it is genuinely a group of negative curvature. Okay, so what do we mean by roughly negative curvature and genuine negative curvature? That is actually part of the precise statement. So I'll just tell you the precise statement. So suppose if G is so some condition, so it is torsion free, so that means there is no finite order element. So G is a group. Okay, so G is a torsion free group. It is Gromov hyperbolic, or sometimes it's called delta hyperbolic. This is what I mean by roughly hyperbolic. So it just means, if you look at the graph or the Cayley graph of the group, it all the triangles on that, if you draw any triangles on that graph, it looks sort of like this thin. Okay, that's a hyperbolic behavior. Okay, so this is a very coarse hyperbolic notion. You can only see this if you go far away from the group. And then once you have a Gromov hyperbolic group, there is a well-defined boundary on the Cayley graph. So that means there is a way to go towards infinity, and on the infinity you have a set sitting inside, and on the infinity there is a set you can construct, and that is called the boundary of the group. And so the third condition is the boundary. So boundary of G is a two-sphere. So that means, so it's a topological space. So it has a topology, and it is homeomorphic to two-sphere. It's just a two-sphere, okay, two-dimensional sphere. Okay, so my group satisfies these three conditions. It's torsion-free, it is Gromov hyperbolic, and its boundary is two-sphere. Then, well, so what are some examples of such groups? It turns out that, so let me give you an example before finishing of stating the conjecture. If you give me any closed, so consider any closed mean compact without boundary 3 manifold. So M3 is compact and without boundary 3 manifold. That has sectional curvature -1. Okay, so this is honest hyperbolic. So historically, when people say hyperbolic, that's what people mean. It's a space with sectional curvature -1. Okay, that's the more classical notion of hyperbolicity. So that's what it is. And if you look at the fundamental group of, so if I give you a manifold without boundary, closed manifold without compact manifold without boundary, and it has sectional curvature -1 everywhere. Okay, if you don't know about sectional curvature, it's just how it's a notion of how curved the space is. Okay, so anyway, if I give you such a manifold, and if I ask you to look at the fundamental group of it, I1 of M3, this is a typical example of a group that satisfies all these conditions. Okay, it is torsion free, it will be Gromov hyperbolic, so its Cayley graph will have thin triangles, and the boundary would be two-sphere. Now, what Cannon's conjecture says is these are the only possible examples. of this kind of groups. Okay, so the Canon's conjecture says if your group satisfy these three conditions, then it has to be something like that. It has to be fundamental group of closed hyperbolic manifold. Okay, so so these are the only example. Then G is the fundamental group of a closed, again closed mean compact and without boundary, hyperbolic three-man. So this is Canon's conjecture, and this is well widely open. For very few cases, people know the answer to this, but mostly this is widely open. So I'm not looking at the chat. So if somebody has a question, please.
I'm looking at it. Yeah.
Oh, okay, thanks.
So,
All right. So
it actually asked this: what is the intuition of this Canon's conjecture? Is there an intuition?
this is almost an unbelievable conjecture to make. I guess the intuition is people don't know the reason behind stating this conjecture. People didn't know any other example of groups satisfying this apart from fundamental group of three manifolds. There is no other way to do that. Well, one reason why people expect this to be true in 3 dimension, because the one dimension lower version is known to be true. So if I give you a group which is torsion free Gromov hyperbolic and its boundary is a one sphere, meaning circle, then it is known by work of Gawai and many other people that it is a fundamental group of closed hyperbolic two manifold. So then people wants to know whether the same thing is true for in the one dimension higher. Okay. Okay, so this is widely open, and so one way to, if you want to understand a conjecture that is hard to attack, you try to find generalization of it and try to disprove those generalizations. Okay, so that will give you the boundary cases, right, where how much you can you go further from it. So this conjecture can be generalized in two directions. One is, instead of Gromov hyperbolic here, I can assume the group to be cat 0. Okay, so cat 0 is a much slightly weaker version, in some sense, weaker version of negative curvature. So instead of Gromov hyperbolic, I could say cat 0. And instead of boundary 2 sphere, I can mention the boundary is embedded in the sphere. Okay, and not in 2 sphere but in higher dimension. So one generalization of Canon's conjecture says if G is, well, again, torsion free. Now cat 0. So cat 0 means the triangle in the Cayley graph looks like an Euclidean, or at most, at least as thin as the Euclidean triangle. Okay, so that's what cat 0 means. So it's slightly weaker than the negative curvature. It's like a zero curvature space, or non-negatively, non-positively curved space. And then the boundary, again, if you have a cat 0 group, it has a well-defined boundary of G is n sphere. Okay. Then G is, well, G is embedded in n sphere. So it's not exactly n sphere, but embedded in n sphere. Then G is virtually fundamental group of a compact n+1 manifold. So here the hypotheses are weakened, and also the conclusion is also weakened. Okay. Okay. So the hypothesis, instead of negative curvature, we demand non-positively curved, and instead of exactly n-sphere boundary, we want the boundary to be embedded inside n-sphere. So with that hypothesis, the conclusion is G is the virtually just means it has a finite index subgroup. That can be a fundamental group of a compact n+1 manifold. Okay, we don't demand any curvature on that manifold. Okay, so that's what in the CAD0 setting, that's the generalization. Even this conjecture is open. Okay, so people don't know what's the well, in n equal to 3 it is open, so I should maybe put 3 here. Um, 2, and this is 3. All right. So what we proved is, well, you cannot do this in a higher dimension. Okay, so this particular conjecture over here does not work in higher dimension. Okay, so probably I should now mention theorem. So for every n bigger than 3, there are torsion-free CAD0 group with boundary embedded in Sn. Okay, so n sphere. So maybe I should write n sphere because that's what I've been writing. But they are not virtually fundamental group of any compact n+1 manifold. Okay. Fundamental group of compact aspherical. So there is another new word. Aspherical means it's a universal cover are contractible. So it turned out if these groups are fundamental group of some manifold, it has to be aspherical. Okay, its universal cover has to be contractible if we assume to be torsion free. So this aspherical condition is not a big condition to have. But anyway, so
you guys? So is this a common theorem? Is this a joint theorem of you and Shrivi?
Yes. Yeah.
Wow, this is a very interesting result. So so sorry for interrupting, but is it? So you guys constructed the group that?
Yes. So
it's a proof of construction. I see.
Yeah, but the I think the hardest work was already done. So there were groups that should have properties like this. We just proved. So these groups are constructed by some other people. We just showed that those groups satisfy what we want them to satisfy. Okay. So maybe I'll for the rest, I'll briefly describe what these groups are, very briefly. So in geometric group theory, if you want to disprove something, there are some usual suspect. Okay, one of the usual suspects is Baumschlag solitaire groups. Okay, they are very simple group, but they have some very wild properties. Okay, if you want to disprove something, you should try this on Baumschlag solitaire group. Maybe Baumschlag solitaire group is your example. Okay, and so the Baumschlag solitaire groups, it goes like this. You have, so it comes with this 2 parameter m and n, and it has this nice description in terms of generator and relation. So you have, it is generated by this 2 element a and t, and the relator you have is, if you conjugate the mth power of a by t, you'd get nth power of a. Okay, so geometrically it is fundamental group of this picture. So you start with a circle and take another cylinder, circle cross I, and then glue one circle with this circle by degree m map, and then glue this other boundary of this cylinder by degree n map, this circle. So that gives you a space. Okay, and if you look at the fundamental group of this space, that turns out to be Baumschlag solitaire group. Okay, now, so this Baumschlag solitaire group almost have all the properties that we want. So it is, well, it is actually one dimension. So its boundary embeds in a 2 sphere, and it does not act virtually on any 3 manifold. Okay, but the problem is it is not CAD 0. Okay, so that's one problem. So if you like negative curvature group, then probably Baumschlag solitaire group is not your group. But to make them CAD 0, Lear elimination very recently in 2021, I think that their paper published in 21, they constructed a similar group, but now a higher dimensional version. So now I'm going to very roughly describe what their group is. So instead of gluing circle cross I, cylinder onto circle, you instead start with a higher dimensional version of circle. So take a torus. Okay, so take a torus and then take a cylinder on the torus. Okay, and now there is a way to generalize this degree m map and degree n map. Okay, but here, since you have the fundamental group is z2, c direct sum z here, so instead of just a one number, it will be given by some 2 by 2 matrix. Okay, so this is, so there is some map a here, some map a prime here, and they are basically 2 by 2 matrix basically. Okay, and it turns out the fundamental group of this is basically Lear elimination group, and they proved that for very mild properties on A, these groups now become CAD 0. Okay, and in fact, not only CAD 0, they retain most of the wild properties of the Baumschlag solitaire groups. Okay, so that means so their main, their paper was their main goal was to disprove many things about CAD 0 groups, and they actually use these groups to disprove all those conjectures. So these are CAD 0 groups, but they have all the wild properties of Baumschlag solitaires, and so they were able to disprove some of the conjectures using this group. So these are our groups. Okay, so instead of one torus, well, 2-dimensional torus, you can instead take n-dimensional torus, and in our theorem this n is that corresponds to the dimension of the torus. Okay, so our group is basically, you have n torus. So I cannot draw n torus, so I'll just write this is n torus, and it looks like this. It is a fundamental group of a space like this. Okay. Okay, so this is roughly what our group is. Now, so our theorem is such groups cannot act on, cannot be fundamental group of n+1 manifold, right? A spherical manifold. Okay, so we proved that. So let me call this group Gn. So prove Gn cannot be fundamental group of a spherical n+1 manifold. Okay. So how does this proof goes? Well, it turns out this whole problem you can boil down to this proving this thing is equivalent to, almost equivalent to proving that there is a so it is equivalent to proving the question that I stated at the beginning of the class. Okay. So remember, at the beginning, we asked this question. So you have this 4-point set, which is embedded inside circle. And I asked whether some bijective map on that 4 points can be extended to the whole circle. It turns out our goal was equivalent to showing, basically we showed this. There is some homeomorphism, that means just bijective continuous map, on Cantor set. If you don't know about Cantor set, it's just some wild set. It's a subset of R. Homeomorphism Cantor set that cannot be extended to circle. So Cantor set can be embedded inside a circle. Okay, it's a nowhere dense set. It has uncountably many points, and there is some action coming from this group Gn somehow on that Cantor set, and what we really proved is that action on this Cantor set cannot be extended to S1, and that proves this theorem. Okay, so in general, this is a very useful questions that you can ask that appears in many contexts. You have a subset and you have a map, so that means you have a way to change that subset in a way, and you ask whether that change in that subset can be extended to the whole thing. Okay, that's what we have to deal with. Okay, so now that we have enough motivation to consider questions like that, so now I can probably give you a proof of this thing. So why this cannot be done here? The proof is very slick, and I learned it from a paper. Can I make it smaller? Okay. So I learned this trick from a paper by Ruska, Stark, and Tran. So here how it goes. So suppose, this the proof goes by contradiction. Okay, so it is, the answer is no. So you cannot extend this cyclic permutation on these 4 points 2n homeomorphism on the whole circle. Suppose you have done that. Suppose you have an extension. Okay. On the contrary, suppose you have a homeomorphism S1 to S1 and its restriction to S, which is that 4-point set, is A. Now, if you have that, what it means is, so the main trick here is to look at the complement of this 4-point. So if the restriction of B is A, then B has to act on the complement as well. So in the complement, you see there are 4 components, right? This interval from 1 to T, this interval from 2 to 3, this interval from 3 to A, and this interval from A to 1. So if there is such map B, then B acts on the complement, so S1 minus S, by preserving, so they have an order, right? So this interval 1 to 2 is beside 2 to 3, 2 to 3 is beside 3 to A, and 3 to A is beside A to 1. Okay, so you have this 4. You can think of this, rectangle sitting there, and this B has to act as a map that preserves this order of these 4 points on this rectangle, and we have a name for that. These are the dihedral group of 4 vertices. Okay, these are the symmetry group of 4 gone. Okay, so I'll just say from the picture, B acts on this violet rectangle. So that means B is a subgroup of the dihedral group of order 4, or of vertices 4, okay, because these are 4 vertices. So D4 is the symmetry group of this thing. Okay, so the subgroup generated by B is a subgroup in D4. But wait, B is coming from this A, right? This restriction of A. Okay, and so its order has to be 3. Okay. On the other hand, D4 has order 8. Okay. So what you are getting is you have a group of order 8 and you have a subgroup of order 3 inside it, which is not possible because 3 does not divide 8. Okay. This is by, again, a non-trivial theorem, Solo's theorem, that says any order of, yes, not exactly Solo's theorem, but the order of the subgroup should divide by divide the order of the whole group. So this implies 3 divides 8. Okay, 3 is because the order of B has to be 3 because the order of A is 3, and 8 here is because the order of D4 is 2 times 4 is 8. And this is clearly a contradiction. Okay, so you cannot have such extension. All right. Okay. So that's all I have. Okay, so
I think this is a really slick way of thinking about it.
Yeah.
One of the things that we could do, I mean, this, for example, this particular trick nicely puts together a bit of topology, a bit of group theory, and in a very simple example, I mean, someone even in high school would be able to understand this within a couple of days of work, right?
Yeah.
So maybe we can have some sessions on this type of stuff.
I really like this proof. Although our proof did not, I was really trying to use this trick in our proof, but somehow I could not manage to do that. But it's a really, it's a really nice trick to prove this. This.
Nice.
Yeah.
Okay, thank you, Arko, for this wonderful start of this. I think many parted series on Cannon's conjecture, and we will probably continue next week on the same time.
Okay.
Uh, I'll see you guys next week, and I'll post the video recording online as well. Thank you.
All right. Okay.
Okay, bye.
See you. Bye.